There are several different types of intermolecular forces, and these are the forces that will hold particles together as liquids or solids. And how strong those intermolecular forces depends on the structure of the molecule. We find that if we have strong molecular forces, that substance is going to have high melting and boiling points. If the forces that attract the particles are weak, it will have low melting and boiling points. So that relationship with temperature, remember temperature is a measure of the average kinetic energy of the particles. So if, say, liquid water is at a higher temperature, the particles in the water, the molecules, are moving faster. And so if they're trying to get through the other Velcro-coated people, or they're trying to escape from the group entirely, the faster they're moving, the more easily they'll be able to escape that stickiness, right? If they're moving very slowly, then it's going to be hard for them to get out. If those forces, though, are not very strong, maybe people are just wearing like corduroy jackets, right? And they're a little bit, they're not slippery, but it'll be pretty easy to slide past each other. Then you don't need as much kinetic energy to be able to move around or to escape. Does that make sense? So all of these intermolecular forces come from interactions between charges of some type. These could be charges of actual ions. They could be partial charges from polar molecules, dipole moments, or they can even be temporary charges on those particles. And this is all based on Coulomb's law, which we've mentioned before. And again, this part, the 1 over 4 pi epsilon naught, we don't need to even think about that. I wish they hadn't put it on there. What we're interested in is Q1 and Q2, which are the charges on the two objects, and R is the distance between them. So the force of attraction is greater when the objects are closer to each other, and the force of attraction is greater when the charges are larger. And we talked about this earlier with fridge magnets, right? If you have one of those really strong magnets, it's going to stick really hard to the refrigerator, whereas if you have a cheapy magnet, it's not going to stick very, very hard. It'll be easy to pull off. The distance here would be like putting pieces of paper behind the magnet, and you get to a certain point. It's not very much distance, is it? It's like 3-4 pieces of paper. Hardly any distance at all, but no, the magnet won't stick, right? So the closer they are, the more attractive they are, and the stronger, the larger the charges, the stronger the attraction. Intermolecular forces are different than bonding forces. We just spent 2 chapters talking about bonding forces. Bonding forces involve large charges at very close distances. Here is a water molecule, and a covalent bond is formed between the oxygen atom and the hydrogen atom, and the distance here is like 96 picometers. With the intermolecular forces, now the distances are on the order of 3 times as great, and so that's definitely going to affect the magnitude of these forces. They're going to be much weaker due to larger distances and due to smaller charges. So the first type of force we're going to talk about is dispersion force. Did you have a question?
Yeah, sorry. Do nonpolar molecules still have they don't really have charges?
Yes, nonpolar molecules do have intermolecular forces.
Okay.
Yeah. In fact, they have this intermolecular force right here.
Oh, okay.
Dispersion forces. So this is present in all molecules and atoms, regardless of whether they're polar or not. They all have it. It's also called a London dispersion force. I've also heard it called induced dipole force, which is the name I prefer. But and so how does this happen? Well, here we have an illustration of a helium atom. We've got the protons and neutrons here, and there's 2 electrons. And this spherical area, that's the orbital, right? The electrons are like a standing wave, and so they're kind of occupying that entire space at the same time. And yet, if you were to take a picture of them, you would force them to behave like particles, and you would see that they are in 2 specific locations. So take a picture here, one there, one here, take another picture over here, third picture. Now they both happen to be on the same side of the atom. Well, that's going to cause a slight imbalance in charge because we have all of the negative charges on one side and no negative charges over here, and so this positive charge is exposed. So now the one side has a partial positive charge and the other side has a partial negative charge. And that can just happen spontaneously. So that is not going to be a very strong charge, right? These partial charges are going to be smaller than the partial charges that we see on polar molecules. And they're not going to last very long either. Well, how does this spontaneous charge inequality affect molecules or atoms sticking together? So we can refer to this as an instantaneous or a temporary dipole. So one molecule happens to get its electrons lopsided. So here is that that atom. The two electrons happen to be over here, and so now this is polar for an instant. This now has a positive end, and if there's a neighboring molecule, the electrons in that neighboring molecule are going to be attracted to that positive charge. And so that will cause this atom to also be a little bit lopsided, and we'll get this force of attraction. So this spontaneous dipole is going to induce a dipole in a neighboring atom. And then that can induce a dipole in the next atom. And so we have this force of attraction here, and that's called the dispersion force. So one of the things I think about, one of my analogies is, imagine you're going out on the San Francisco Bay on one of those blue and white cruises or something. You're going to go out in the bay and you're going to see Alcatraz, right? So everybody's standing around on the deck and people are kind of spread out and the boat's nice and level, right? And you get over and you get closer to Alcatraz, and then everybody wants to get on the side of the boat where Alcatraz is so they can see it, right? Because that's why you took the cruise, you wanted to see Alcatraz. So everybody goes over to that side of the boat and it might tip just a teeny tiny bit, right? Well, what if there's a neighboring boat and they see that boat tipping? They're like, ooh, and everybody wants to go over and see the boat tip over, right? And then they're going to tip a little bit and the next boat over going to do the same thing, okay? So that's kind of the idea. Any questions? How strong that dispersion force is depends on how easy it is to push those electrons around, how lopsided, how easy it is to get them lopsided. Last night we only had 4 trains instead of 9. I don't know what was going on. Anyway. So in a large electron cloud, the electrons are further away from the nucleus, and I kind of think of it as like, Santa Claus's belly, a bowl full of jelly, and it's just all floppy and flabby, right? And so it can get lopsided more easily than a small atom where the electrons are really close and they're tight, okay? So the bigger the atom or molecule is, the more easily the electron cloud can be polarized. And so we see that the dispersion force generally increases with molar mass. You can only do this when you're comparing atoms or molecules that are similar to each other. But here we're comparing noble gases. As we go down from helium to xenon, the noble gas atoms get larger and larger. We can't really measure the dispersion force itself, but we can observe the boiling point of these liquids, which is related to the strength of the dispersion forces. Because the stronger the dispersion force, the higher the boiling point. So here we see that the smallest atom, helium, has the lowest boiling point, and the largest atom has the highest boiling point. And that's because those electron clouds are more easy to polarize.
Does that affect melting to freezing point?
It affects melting, freezing, yes, as well.
Does it go up or down? It goes up?
Same direction.
Same direction, okay.
Yeah, we don't talk about the melting point here because I mean helium to get to a liquid is down at 4.2 Kelvin, and 0 is the coldest you can possibly get. So yeah, good luck getting solid helium, right? You'd have to get to absolute 0 to have that. So the shape of the molecule also plays a part. So here, comparing two molecules that have the same size, the same molar mass, right? And one of them has more of a linear shape, and one of them has more of a spherical shape. Now, if you think of these as being covered in Velcro, and think about, well, which ones are going to stick together better? If you have these two long ones, they have a larger area for interaction where the Velcro can contact the Velcro on the other object, right? And they're going to stick together better. Whereas if you have two spheres, they can only touch at one point, very, very small area, and so they're not going to stick together as well. So even though the magnitude of the dispersion forces are the same for these two molecules, the effect here is smaller for the neopentane because of its shape. So neopentane, the spherical shape, has a boiling point of 9.5 degrees Celsius, and N-pentane, that's more linear, has a boiling point of 36. So these molecules have to get a lot more kinetic energy before they can start sliding past each other or escaping into the gas state. This is a graph just showing the boiling point as a function of molar mass for some comparable compounds. We see that as the molar mass increases, so does the boiling point, and that illustrates that the strength of the dispersion force is larger in the larger molecules. So this is a kind of question that you should be able to answer. Which halogen has the highest boiling point? So a high boiling point is that going to be large, strong intermolecular forces or weak? It's going to be strong intermolecular forces. So we've got Cl2, Br2, and I2. Which one is going to have the stronger dispersion forces? Iodine, because it's larger, right? So the I2 molecule, iodine is 128 grams for each of them, compared to bromine at 80 and chlorine at 35. So because this is larger and more easily polarized, we expect that it would have stronger dispersion forces and therefore higher boiling point. Any questions?
Sorry, like with ionic compounds, they have is that a different reason why they're harder to why they have a higher boiling point?
Yeah, so an ionic compound really doesn't have intermolecular forces. It's held together by ionic bonds, which are far stronger than the intermolecular forces.
So it has to be covalent in order for it to experience.
The intermolecular forces are going to be between atoms and covalent molecules.
Okay.
Yeah. So like, table salt, sodium chloride, you can think of one crystal of table salt as being essentially one giant molecule, and it's all connected with ionic bonds, and so it's going to have a really, really high melting point.
Okay.
Yep.
Those are stronger than.
Much stronger.
Okay.
Yep. So the next type of force is called the dipole-dipole force. It's a force of interaction between two dipoles. So these exist in all molecules that are polar. So in the previous chapter, we talked about shapes of molecules and polar bonds and how to identify whether a molecule was polar or not. And that's going to help us in this chapter. So dipole-dipole forces are stronger than dispersion forces because polar molecules have permanent dipoles. Instead of the dipole coming and going and being induced by neighboring molecules, these molecules always have dipoles, and so that charge is always there to attract something else. So here we're looking at a space-filling model and then an electrostatic potential model of the same molecule. And so this is a polar molecule. One end is slightly negative, one is slightly positive, and we have attraction between the negative and positive charges of neighboring molecules. So polar molecules have dipole-dipole forces, but they also have dispersion forces. If we look at polar molecules and compare two polar molecules of similar size, we want them to be in similar size because we don't want the difference in dispersion forces to cause a difference in the melting point and boiling point. So these guys, almost identical masses. This molecule is polar, so the carbon, the central atom, has no lone pairs, but oxygen is one of the groups and hydrogen are the other, so they're not all the same. This is a polar molecule. This ethane has just carbon-hydrogen and carbon-carbon bonds. They're all nonpolar bonds, nonpolar compound. So the boiling point for formaldehyde, the polar substance, is negative 19.5 degrees Celsius, and for ethane it's negative 88. So the ethane, the nonpolar one, has a much lower boiling point because it only has the dispersion forces, whereas the polar molecule also has dipole-dipole forces. Any questions? It's a graph showing boiling point as a function of dipole moment. Remember, dipole moment measures the difference in charge between those two ends of something. So the larger the dipole moment, the more polar it is, the higher those partial charges are. These compounds are all similar in mass, and we see that as the degree of polarity increases, then the boiling point increases also. Polarity of molecules is important in determining miscibility. So that might be a new word. And it sounds a little bit to me like mixability, which is not a word, but would be easier to guess what it means, right? The ability to mix, right? So miscibility is the ability to mix without separating, and it's usually used in reference to liquids. So if you take alcohol and water and you pour them together, they will mix together just fine. They are miscible. If you take oil and water and mix them together, they will separate into layers because one is polar and one is nonpolar. Here we have an example of pentane, which is nonpolar, and water, which is polar. So water has dipole-dipole forces. The forces of attraction between the water molecules are much stronger than the forces of attraction between the pentane molecules. And the force of attraction between pentane and water is going to be really, really small because pentane only occasionally has an instantaneous dipole and then it disappears. So these water molecules are very much attracted to each other, almost like magnets, and they're just going to kind of click together, and they're really going to squeeze out the pentane molecules that they're not attracted to. And so the pentane's going to sit in a layer on top because it's less dense than the water. So our saying that we use to help us remember this is like dissolves like. So if you have two substances that are polar, they'll probably be miscible. Two substances that are nonpolar, probably miscible. If you have polar and nonpolar, they're not going to mix. Yeah.
Do molecules that have dipole-dipole force, do they still have dispersion force?
Yes.
Like an addition?
Yep.
Okay.
Yeah, they also have dispersion forces.
So they're together. Okay.
Yeah, so if you compare two polar molecules and one is much bigger than the other, you can see the effect of the dispersion forces because the boiling point will be higher in the larger molecule. Yeah. Which of these molecules have dipole-dipole forces? So Ci4, I wrote the name out because this is not chlorine 4, this is carbon tetraiodide. CH3Cl or HCl. So we're trying to identify which ones have dipole-dipole forces. What kind of molecules have dipole-dipole forces? Polar molecules. So we're looking for polar molecules. Let's write with a pen instead of a highlighter. So we're looking for things that are polar. So let's not bother to make the entire Lewis structure, but just think about the skeleton here. So we got that guy, and we got this guy, and we got this guy. How many bonds does carbon like to make? 4. So is this carbon going to have any lone pairs? No. So there's no lone pairs on the central atom, and are all the atoms bonded to it the same? Yes. So is this polar? No, this is nonpolar. So does it have dipole-dipole forces? No. How about this one? Again, we have carbon with 4 bonds. There's going to be no lone pairs there. But now we have chlorine here and 3 hydrogens. So is this polar? This is polar because chlorine's different than the hydrogens. So this one's polar, so that one's going to have dipole-dipole forces. How about HCl? Polar or nonpolar? That one's also polar. So if you see 2 identical nonmetals like nitrogen and nitrogen, that's definitely nonpolar. If you see 2 different nonmetals, most likely it's polar, and on exams and anything that matters, that's what I expect you to answer. So because these are 2 different elements, we would predict correctly that their electronegativities are different, and this is a polar molecule. Any questions? Here we're looking at the molecule acetonitrile, which has this formula. There's an electrostatic potential map for it. This is a polar molecule. This is the nitrogen end, which is going to be negative, and the hydrogen end is going to be positive. So this is asking us which of these 4 combinations, 4 orientations, is going to represent how 2 acetonitrile molecules would interact with each other. So are the positive ends going to be attracted to each other? Positive and positive attract? No. What if the negative ends are together? That's not good either. We want positive and negative, right? So which of these shows the positive end of acetonitrile next to the negative end? It can help to draw those arrows. So the nitrogen end is more negative. It's more attractive to the electrons, and so the arrow points that way, and this end is positive. So then this one is like that, and here we've got this. So in D, we have the negative ends together. That's not going to be good. Here, these just are kind of at odds with each other, right? There might be some attraction here, but they're probably not going to line up that way because this nitrogen doesn't want to be next to that nitrogen. Here, we've got the negative ends awfully close together as well. So this A is how we would expect them to be oriented. The positive of one next to the negative end of the other. Third type of intermolecular force is called hydrogen bonding. What this is like dipole-dipole force on steroids. It's a super dipole-dipole force. It's the same idea, it's just a lot stronger. So hydrogen bonding is found, again, in polar molecules, but it's polar molecules where we have hydrogen bonded to fluorine, oxygen, or nitrogen. These 3 atoms are special because they are small and very electronegative. So their partial charges are fairly large, and because they are small, the atoms can get close to each other. So we have Q1, Q2 being higher, and R being smaller. So this is an HF molecule. Here's the hydrogen, here's the fluorine, and so we have this negative end of this molecule here and the positive end, and those will be attracted to each other. This attraction is stronger because those partial charges are larger and the molecules are able to get closer to each other. So how do you remember this? E.T. wanted to phone home. Okay. Fluorine, oxygen, or nitrogen bonded directly to hydrogen. Those kinds of molecules will have hydrogen bonding. Here we have examples of hydrogen bonding in ethanol. Here we have oxygen-hydrogen bond, right? Phone home. Any one of these bonded to hydrogen. So the hydrogen bond is not the bond between the hydrogen and the oxygen. That's a covalent bond, and it does involve hydrogen, but it's not called the hydrogen bond. The hydrogen bond is the electrostatic attraction between the hydrogen of one molecule and the oxygen of a neighboring molecule. So these guys will have hydrogen bonding. Here we have water molecules. Water molecules have oxygen-hydrogen bonds. They're polar. And so the hydrogen bond, again, is between hydrogen on one atom and hydrogen on one molecule and oxygen on a neighboring molecule. So hydrogen bonds are between molecules. Chemical bonds are between atoms within the same molecule. So we call these hydrogen bonds, but don't get them mixed up with regular chemical bonds. Hydrogen bonds are only 2 to 5% as strong as a covalent bond, so they are much, much weaker than covalent bonds. Here we can look at ethanol and dimethyl ether. Both of these compounds are polar. Let's just look at the Lewis structure because it's not obvious there. So that's ethanol. Dimethyl ether has the same number of carbons and hydrogens, but they're arranged differently. So here we have oxygen and hydrogen. On this end we have an oxygen-hydrogen bond, so we could have hydrogen bonding. In this molecule, even though it's polar, there are carbon-hydrogen bonds, but that's not part of phone home. There's no C in there. Hydrogen is bonded to carbon, but that's not a polar bond even. There's oxygen here, but it's not directly bonded to the hydrogen. So this is a polar molecule. It'll have dipole-dipole forces, but it won't have hydrogen bonding. So if we look at the boiling points, ethanol boils at positive 78 degrees Celsius, and dimethyl ether boils at negative 22. There's a huge difference because of the hydrogen bonding. Both of these are polar, and they're the same size. Any questions? Melting points will also be higher with hydrogen bonding. We are accustomed to living with water. It's very much necessary for life, and we swim in it, and we drink it, and we take baths in it, and all kinds of stuff. But water is actually a very strange molecule. It has an extremely high boiling point. So if we look at the other group 6A elements and the compounds that they form with hydrogen, H2S, H2SE, and H2TE, we see there's a trend here, right? These are all polar molecules because there's lone pairs on the central atom. as the molar mass of these molecules gets larger, the boiling point goes up, right? And based on the molar mass of oxygen and hydrogen, we would expect the boiling point for water to be down here, like minus 85, 90 degrees Celsius. If that were the case, at room temperature, all water would be in the gas state. Your body contains a lot of water. That wouldn't work if it was all in the gas state, would it? But because of the hydrogen bonding that water experiences, those molecules are held together much, much more strongly than the molecules in H2S, and so its boiling point is plus 100 instead of like minus 85, which is just huge. If we look at group 4A and the hydrides of that, again, we see kind of a trend here, whereas the molar mass increases, the boiling point increases, and that can be attributed to the increase in dispersion forces based on mass. When we get to the smallest one here, CH4, it's not on the line either, but it's not above the line like hydrogen and oxygen were. It's actually below the line because this does not engage in hydrogen bonding at all. It's nonpolar. It only has dispersion forces. Any questions? So this is a kind of a question you should be able to answer. Which has the higher boiling point, HF or HCl? And the dreaded question, why? HF and HCl. Higher or lower boiling point, melting point, these questions are going to be answered by looking at what types of intermolecular forces do these compounds have. And that's based on, are these molecules polar or not? Are these molecules polar? Yeah, they both are because they're diatomic. There's just two atoms, and they're two different elements, and so that's a polar bond. There's only the one polar bond. If the bond's polar, the molecule's polar. So both of these have dispersion forces because everything has dispersion forces. These are both polar, so they have dipole-dipole interactions. So far they have the same kinds of intermolecular forces, but we have that third type, hydrogen bonding. Can either of these engage in hydrogen bonding? Yeah, the HF, it has a hydrogen-fluorine bond. So this also has hydrogen bonding. Hydrogen bonding is super dipole-dipole force. I mean, it's like really, really a lot bigger. So which of these is going to have a higher boiling point? The HF. So HF is going to have the higher boiling point because it has hydrogen bonding in addition to the other types of intermolecular forces. There's a fourth type of force here, which is not technically an intermolecular force. It's called the ion dipole force, and it is important. So this is a force that occurs when you have an ionic compound that is mixed with a polar compound. So something like table salt being mixed with water, right? Ionic compound and a polar molecule. Ion dipole forces are very important in the formation of aqueous solutions. They are stronger even than hydrogen bonding. So here we have the chloride ion from sodium chloride. And if you think about sodium chloride trying to dissolve, we've got chloride ions, and we've got, I guess they're purple, we've got sodium ions. And these are +1 and -1, much bigger than the charges that we see with even hydrogen bonding. And so these guys are attracted to each other. So this guy has chlorines, on all sides of it and is pretty happy there. So why would it leave and go off into the water by itself? We have to replace the attraction that it has in the ionic compound with some other type of attraction. So water has a negative end and a positive end. Well, the negative end of water is going to be attracted to the positive ions. This doesn't have a full negative one charge, but if you get a bunch of water molecules around it, together their charge can add up to -1. And so a bunch of water molecules can surround this sodium and make it feel comfortable, right? It replaces the attractions it had in the ionic crystal. And the chloride also gets lured away and feels comfortable with the water because the water's going to show chloride its positive side. So water is two-faced and lures ions away from each other. Any questions? Yeah. Mm-hmm. Yeah, it breaks it apart. This is a summary of these types of intermolecular forces in order of strength. So dispersion forces are the weakest, then dipole-dipole, hydrogen bonding, and ion dipole. But there's an asterisk for dispersion forces. Dispersion forces can be very strong, as strong or even stronger than the others for molecules of very high molar mass. So when you are asked to compare different compounds for boiling point or melting point, those compounds are chosen very carefully. We're not trying to trick you there. But if you wonder, well, why is this fat that is all nonpolar, why is that a solid at room temperature, but water is liquid? Doesn't water have hydrogen bonding? Well, yeah, water does have hydrogen bonding, but those fat molecules are really, really big. And so their dispersion forces are stronger, and they're actually a solid at room temperature instead of a liquid. But when you're comparing similar compounds, this is the order. And these are the types of molecules that have these different interactions. So of these, which substance has the highest boiling point? Again, we're looking for strongest intermolecular forces. What's the strongest one that these could have? This one by itself can't have ion dipole forces, can it? Because that requires an ionic compound and a polar compound. So here we're looking for dispersion forces, dipole-dipole forces, or hydrogen bonding. If we're looking for highest boiling point, are we looking for strongest or weakest forces? The strongest. These are all in the same ballpark in terms of size. They're not exactly the same. But, this one's 28, and that one is what? Also 28, right? So they're really close. It's not like this is 500 and that one's 28. Roughly the same size. So let's draw this out because it really helps to see where those bonds are. When it says CH3, that means that those 3 hydrogens are bonded to that carbon. And then we've got hydrogen and oxygen. On this one, you just got carbon bonded to oxygen and nitrogen bonded to nitrogen. Do any of these have hydrogen bonds? Yeah. This one does, because it has a hydrogen-oxygen bond. These guys don't even have hydrogen, so they can't have hydrogen bonds. So this is going to have the highest boiling point because it has the strongest intermolecular forces. Any questions? Intermolecular forces are really important in biological systems. Your DNA is held together by hydrogen bonds. And the way the base pairs hydrogen bond with each other allows DNA to replicate itself. So DNA, we've got a phosphate sugar backbone with bases attached to it, kind of like charms on a charm bracelet. And these are the different bases that are present in DNA. There's thymine and adenine, cytosine and guanine. Thymine and adenine will always pair together because they can form 2 hydrogen bonds with each other. Cytosine and guanine can form 3 hydrogen bonds with each other. And so they're just like super attracted to each other and they just go click and they stick together. So here's your DNA, which is 2 strands with complementary bases on each side. So the T is always paired with A and G is always paired with C. To replicate the DNA, you separate these 2 strands and then you bring in the base pairs and tie them together with that phosphate sugar backbone. So over here, as we're making this new strand, for A T is going to come in and stick to that because they match to each other. Here, this A is coming in and is going to stick to the T. Another A or G or C is not going to fit together. Here they're showing you with a little curved surface and kind of a pointy surface. And so these 2 match like puzzle pieces. So that comes in and sticks there, and then it's tied together with that phosphate sugar backbone, and now we have 2 identical strands of DNA from the one strand. Really, really cool. Not a big fan of biology, but I love biochemistry. Any questions? Intermolecular forces are also really important in the shapes of proteins. Proteins are really, really large molecules, and they're all kind of twisted up on themselves in a particular conformation, and they are held that way by intermolecular forces. If you heat a protein, then you disrupt those intermolecular forces, and we say it's denatured, and sometimes it can recover from that, but many times it can't. So if you think about it like an egg white is a lot of protein. If you heat it on the stove, it becomes opaque and solid, right, instead of kind of clear and runny. And that's because you've denatured the proteins. And that's all about the intermolecular forces.